going to start. All right, great. So welcome back, everybody, to the second and third lectures for the my course in arithmetic harmonic analysis. Last time we introduced the circle method, and in particular, we are focusing on sums of squares in 5 or more dimensions. So we proved that the bound we expected to be true, or the bound that Hardy and Littlewood proved, is going to be essentially the right order of magnitude by just a very simple divisor argument, and by getting some upper bound, right? So this right here, S of n, is the number of integer points on a sphere of radius square root of n, centered at the origin, and the number is just counting, right? It's the cardinality of that set. So we found out in 4 or more dimensions that we have an upper bound of this shape, right? So it scales like n to the d over 2 minus 1 instead of n to the d over 2 minus a half, right? So square root of n is the radius. So if it was growing like the area of the sphere, then you would expect d minus 1, or in this case, n to the d over 2 minus 1/2. But it's actually appreciably smaller, the number of integer points, right? As we've already seen by a very simple divisor bound. So again, the key insights, one of the key insights in Hardy and Littlewood's work was that you can rewrite the integer points as summing up a bunch of delta functions and evaluating it. Oh, I have something in the chat. Someone asked a question. There is a tool pop-up covering part of the slides. Thanks. Oh, okay. Great. I just learned how to minimize it. Thank you, Tom. Yes, sorry. So I was saying, so one of their great ideas was that you can use this delta function to rewrite the indicator function at any point. And for them, this is 100 years ago, right? So for them, complex analysis is sort of a pretty new tool that had been really well developed over the preceding 20 to 40 years. And they chose to do this by looking at the residue theorem and relating the generating function to theta functions. Okay, so the more modern point of view that we're taking is actually this oscillatory integral representation, where, if you remember, this e of nt means it's e to the minus 2 pi I times nt. So this delta function is just, it's 1 whenever, so this integral is always 1 when n is 0, and it's 0 whenever n is non-zero. Okay, so it's very good for picking out the origin inside the integers. So we wrote down a generating function by just formally taking all these exponentials and replacing the n with n squared. And then when I took d copies of them and multiplied them together, it turns out you write this, that turns out to be the sum of the squares in n variables. And if I could just put all the ones that, such that n squared added up to n together, I got this representation function, right? And then formally applying this delta function over here, I could see that whenever I multiply against e to the minus nt, I'll pick out r to the n, or sorry, r of n. Okay, so that's where we were at last time. And we did this we made this formal argument rigorous by smoothing all of the sums. So I localized to some box of radius 2r, and it's going to be 1 inside from minus r to r in every dimension, in every direction, sorry. And when you do that, you can actually get the finiteness you need to show that the representation function, to analyze the representation function you want. Okay, and in doing so, we introduced this function, hr of t, which is supposed to capture this phi of r right here is capturing exactly the range of that support. So the picture I had in mind, and if you cannot see this, please protest, is just as a profile, I had my initial bump function was from minus 1 to 1, right? It's 1, oh, so it's 1 here, and then it quickly decays out to 0, between minus 2 and 2. Right? And then I rescale that by just, dilating by r. Okay, so phi of r just divided by r. Right? just scale it all out. And this is a nice smooth Schwartz function. It's compactly supported, it's one in the range we care about, and it quickly decays to 0 outside of it. But this dilational factor is important for us, and we have to study the effect it has. Okay. Just some quick feedback. Could anyone see that? I can't see anyone's.
Yeah, it was visible.
Great. Okay, cool. Because luckily I don't have my stylus, but luckily I have a blackboard. So make use of that when appropriate. Yes. Okay. So we went through some of the smoothing, and I won't recall that. And we also went through some heuristics of the circle method, which are very good to recall, actually. We saw that when you take t equal to 0 in our exponential sum, which I'll just rewrite as well, the exponential sum we care about, this one. And we see that when t is equal to 0 in this, all of these terms are 1, all of these exponentials are 1. And so we're just picking up a bunch of positive terms. And those positive terms are about the volume of that cube, which is of course r to the d. Okay, but when t is equal to a half, then if you just pretend you have a sharp cutoff for a moment, so you ignore some edge effects, then if t is a half, what you get for a single one-dimensional sum, for instance, sum from n equals minus n to n dn squared t, well, this is going to be plus or minus 1, depending on n. And that came out because, well, the squares are evenly distributed, right? If you're even, n squared is going to be divisible by 4, and so this term will end up being a 1. And if n is odd, n squared is odd, so this will end up being a minus 1. And then you're just adding up pairs of plus 1s and minus 1s. And at 0, of course, you have just a single term that's 1. So we see that in this graph here, which is supposed to map this function for n being about size 100. No, sorry, 10,000. And looking at rational points whose denominator is 1 over 100. So we see this big peak at the origin. At 1/2, we see it's basically 0. And then we see at some other rationals, prominent rationals, such as 2/5, 3/5, 4/5, 1/5, so on, that we get some other peaks here. Okay. And moreover, it's pretty smooth in between because these exponential sums are trigonometric series and therefore C infinity. Like periodic, but C infinity. So we discussed that, and then here's another sort of finer scale version of that one, where I increased n to about 10,000 or something. So just to recover the structure of the proof before we start getting into the details. First, we're going to use our oscillatory integral formulation so that we actually analyze this exponential sum. And the way we're going to analyze that exponential sum is we're going to look at we're going to use the fact that around each of these small rational points, small meaning the denominator is small when you've reduced the fraction. We know that it's going to have a lot of structure there. It's going to usually be quite big. And we study around those points, and we're going to do so by Poisson summation. And this introduces a dual lattice where we study frequencies on. And it turns out that the frequency at the origin, the 0th frequency, is the biggest one. And the rest we're going to put into error. Okay, that's pretty good when Q is small, actually, but when Q is large, it's much less efficient. The way Hardy and Littlewood got around that was by using modular forms, but we're going to not use modular forms, and we're going to use this more modern way of smoothing. And for us, that brings into the second great idea that Hardy and Littlewood had in this work, and that's splitting things into major and minor arcs, which correspond exactly when Q is small or is not small, respectively. On major arcs, we do step 2, the Poisson summation and everything, and find the 0th frequency, study that, throw everything else away. But on the minor arcs, it turns out there's enough noise. It's already quite noisy. And so there's a lot of cancellation in it that you can show directly by Weyl's inequality. And then we're going to have to optimize what it means to be a major and minor. Okay. Then there's the rest of the proof is optimizing the major arcs so that you can actually find out what that optimization between major and minor is. So the rest of the operations or the parts of the proof are pretty much interchangeable. We need to extend the major arc to get a full singular integral, and then we need to extend the singular series that pops out to get a product of p-adic singular integrals. And we have to show that each of those things is positive and then doesn't grow too large. Or it's also big enough, right? If you have an infinite product, then you better make sure that each term is and the tail is tending to 1 and tending to 1 quickly enough. If it's tending to 0, then your series is 0. Your product is 0. Okay, so that was what we covered last time, and then we started getting into the Farey dissection. So the Farey dissection for us is just going to be a convenient way to chop up the unit integral, right? So we have R mod z, which are identifying with 0 to 1, the fundamental domain from 0 to 1. Okay, and at 0, we have some big major arc because 0 over 1 is the smallest modulus we could have. That's going to turn out to pick out some arc here. And it wraps around, right, because this is R mod z. So we get some arc there, then around 1/2, we get some slightly smaller arc. And around 1/3, we get something smaller, and 2/3, and then 3/4, and so on. But the way we're going to do that is we're actually going to make these intervals, which I've sort of drawn symmetric about, at least where I'm thinking 1/2 is, right? They're going to be a little asymmetric, and they'll be done by the Farey sequence, as on the screen. The Farey sequence just starts by writing down all the reduced fractions up to some height x, or level x, where x is the denominator, the biggest possible denominator, arranges them in order, increasing order, and then defines these intervals that actually partition this up. Now, we don't care too much about it, but it is an exercise in elementary number theory to show that if you have an arc I of a over q, then its length is basically up to some constants, 1 over q times x, where x is that level, the biggest possible denominator that we have. Okay, and this here, of course, just meant again, it's something like 1 over 4 times q over x and 4 qx. So that's what I meant by these arcs have length essentially 1 over qx. And a priori, the I bar, it's centered at a over q. Great. So if you're not familiar with it and you don't feel like proving that, it is in Hardy and Wright on their section and Farey sequence. That's sort of a very minor detail in the rest of the argument, so I'm not going to go into that. So we do break up this integral, right? Now we have an integral over t, over the torus, R mod z, and we break it up into a sum over each piece on this arc. So for each denominator q, right, I have all the fractions a over q, where a is coprime to q. And that's what u sub q means. It's just all those a's between 1 and q that are coprime to q. And then I of a over q is that corresponding Farey arc. All right. So the way we're going to start using Poisson summation is we shift our I of a over q, which is centered at a over q, to the origin so that we can start uniformizing our analysis, okay, for each arc. And it's not quite symmetric about the origin, but it's very close to it. So when we do that, we end up getting an integral of this shape. So it's a series, right, where I've taken in this first line. To get to the second one, all I've done is I've shifted by a over q, so that I broke up the sum of I bars up into i's. And then I just follow the change of variables so that, this turns into multiplication. We can pull out this factor right here. And what I'm left with is this following integral that we need to process. Lovely. So again, we're going to process it using Poisson summation. And to do that, I need to rewrite my exponential sum, this one, so it's written actually as some sort of Fourier series, and to apply Poisson summation, I need to write it. So I need to make that very explicit and write what the dual of it is. So that introduces a little bit more notation. In particular, I write each of these terms. So this is that definition, but then this is just h sub r t of n. Because this is depending on n as a point in ZD. Right, so Poisson summation then says that this is just, so it's equal to the sum of h r t n, right, and ZD. Poisson summation says you get to put the Fourier transform all over it. The one over r, thinking about this HRT as a function on r. Sorry, RD. Great. Now to do that, so to actually use that in practice, we have to remember that we've put in the shift for each of these HRTs. So each one has a plus A over Q that we have to keep in track over here. Okay. This Fourier transform right here is with respect to RD and is just in the variable n. It's not on T. But how we apply Poisson summation will depend on A over Q. On this shift that's in there. And when you do it correctly, I've written down the result for the moment. So you see what flavor we get. When you do that, you end up getting the following down here at the bottom. So again, there's some dual lattice, and in ZD, what that dual lattice is the following. So let me just draw this over here. Hopefully it's still visible. This is our little Schwartz function P. And so on ZD, we break up our sum over n and ZD into a sum over m in ZD and a sum over b in Z mod Q D. And where we think about n as equal to Q times m plus d. So what that looks like diagrammatically is if Q is say 2, then I've actually used this sublattice where I have an index of 2 in each direction. What that means in the Poisson summation is you get a dual lattice where it's now 1/2. Instead of, the dilation is by a half instead of 2 by duality. That's where we see these frequencies coming up here in the bottom right. And the effect this shift by A over Q has, as well as the decomposition of the lattice into these bigger tiles, is you get some exponential sum that looks like this. Okay, so the expression down here, Q in brackets to the D, is just the integers from 1 to Q in each coordinate. And this is still just the sum of squares of BI. And then this is the product of the sum of BI times MI. When we see the A over Q from the shift popping up right here. So these are actually normalized d-dimensional Gauss sums. Normalized because the factor of Q to the minus D that pops out from following the normalization, the Euclidean normalization, gets bundled up with it. And it's normalized in the sense that, well, it's just trivially, it has a bound of at most 1. And that's just followed by, I go into the sum and I just apply the triangle inequality, absolute values, triangle inequality to make all of these buddies right here, absolute value 1. And so I'm summing up q to the d things normalized by q to the minus d. One important fact that we'll use later to simplify a bit of our analysis is each of these d-dimensional Gauss sums is actually just a product, a tensor product of one-dimensional Gauss sums. And you see that because this, again, this absolute value squared is just a sum of bi's. This is a minus a sum of bi times mi's, and you get the sum in the exponential turns into a product over the i's. So any bound that I'll be able to prove on the Gauss sum for one-dimensional Gauss sum automatically bootstraps to a d-dimensional version. Now we've just seen here a very trivial bound of 1. Now I've just rewritten what I had before that Gauss sum in terms of this notation. All right. Oh, I have lied. I did not recall Poisson summation for you. Okay. So I'll come back to that later then. I'll fill that in. I'll fill that gap in later. Please just take for granted at the moment that this is actually what happens when you follow Poisson summation. And again, the main idea is to break things up into tiles based on your modulus Q. Great. Are there any questions at the moment? Okay, I can't see anyone, so I assume it's cool. It's all kosher. So carrying on, skipping the actual work of doing Poisson summation correctly. Let's process this exponential sum a bit more now that we have a certain shape to it. Okay, now that we've done something on trivial Poisson summation, let's see what that gives us. So we started with the fact that these functions right here were smooth, and they also decay because phi decays. Since phi is Schwartz and E is C infinity, this is actually a Schwartz function. And what we expect is each of these, when we take the Euclidean Fourier transform, should also decay quite well in terms of n. We have one small snafu there in that this n is being abated a bit by the q, the denominator, the fraction a over q. Then the denominator sort of shrinks the lattice on the dual side. So we are expecting this, but there's a bit of a catch because anything that's, so we think anything that's non-zero, so as in the limit, as n increases, or as I've written here, c increases to infinity, we should expect decay of this Fourier transform. And that's true. But every time we apply this for each a over q, we're getting close to infinity takes longer to do because q is shrinking the scale. So there's a bit of a competition there between the two. Anyways, we're going to still hope for the best and expect this approximation. That really the thing that matters is the zeroth frequency. I can discard all the non-zero n in this exponential sum and therefore in this integral. Then once we do that, we extend the range from the integral of I over q to all of r. And that is something that now just depends on n and r, the big N that I'm trying to count the number of representations for, not the one running over a lattice, ZD. So here's the bound that we can get for the Fourier transform of HR. It's going to depend on T and R, and of course C. Now we really care about the dependence on C, since H is Schwartz, right, and HR is therefore Schwartz. We expect arbitrarily good decay, and indeed we see that in terms of C as good polynomial decay. Whatever n you give me, and this, unfortunately, I wish I had my stylus here. This n is not at all the one we're trying to represent. It should be some m. It's just a big natural number. Sorry, that you get to choose whenever you need to in the argument. So some big natural number, we get that all orders of decay that we want for C. But we pay a penalty in terms of R and T. So initially you would think, this first factor is canceling out R quite rapidly, but it's actually offset by the second one. So if T here isn't small enough, say it's at least size 1 over R, then I have picked up a factor of R here. That's completely canceled out this savings here. Nevertheless, this will be useful, so let's prove it. So the first bound, which is almost always the easiest one to prove, is the low frequency bound. If I'm looking when C is small, say less than 10 to the 10d, still some finite number for each dimension, then there's some constant such that this is always at most R to the d. Why is that? That's just because this, let's write down what the Fourier transform is. This integral, right? And these are two exponentials. I can just combine them together. And that's sum. We apply the triangle inequality again by just moving the absolute value inside. When I do that, this is less than or equal to RD, and we'll 5x over R. This is a non-negative function, so I can really just, it's the same as this. And again, this is 1 on a cube of side lengths minus R to R. And it's supported in one that's from minus 2R to minus 2R to 2R. So this is actually R to the D. When C is small, you see that this bound comes out. Right. And that's C any finite number, really. It just changes the implicit constant that I haven't written down in here. The point is that the proposition is really a statement about what's happening at infinity. And so we really care about what happens when C is quite large. So the principle of non-stationary phase comes to the rescue. And this, of course, was something that was known to Hardy and Littlewood. They used it quite effectively, and it was one of the sort of foundational techniques of complex analysis at the time. Luckily, there are real variable proofs of it now, and it's really just integration by parts. All I do is I do a change of variables where I send x to r times x. So I pull out that factor of r to the d that we saw at the front, and I'm left with an expression that looks like the second line. I move the r's onto the c or the t's and so on, and I apply integration by parts where I'm thinking this is the thing that was differentiated. I need to move the derivative off of the exponential onto the function phi. Okay, but it's actually phi times this quadratic exponential. I'm moving the derivative off of the linear exponential over here. when you do that, when you integrate by parts, you just pull out factors of r times c in terms of x, right? That's where this comes in, and I get to do that. I can integrate by parts n times, and I'm just taking the directional derivative in terms of c for this other function, and that should be that should be these should all be r to the d's. It's integrals over r to the d. And of course, when you do that, what you're left with is just this bound, actually. Because it's this phase that's really blowing things up. Phi is fixed, so all of its derivatives are fixed and it's Schwartz. That's a well-controlled thing. But these r squared times t are really messing with you. All the implicit constants that arise are something like 2 pi I to the n. And so when you take absolute values and everything, it's just 2 pi to the n. So this implicit constant actually grows exponentially in terms of, or polynomially in terms of the number of times you integrate by parts. So are there any questions on this proposition, what it means or why it's useful? Or sorry, how it's proved? Everyone's happy. Great, great, great. So as a corollary, when t is quite small, this is good for us. The bound we had depended on how r squared relates to t as well as to c, as what's happening with c, right? But when c, in terms of c, you can always, as you increase n, the bound in terms of c is just getting better and better for you in terms of summing up. And the real hindrance for us is what's happening at the interplay between r and t. So if t is sufficiently small, it turns out that you just get a bound of this shape, and this should be absolute values here. So basically, it looks like something that if you fix your Farey height to be x, which we have, then you get a bound that depends on how the Farey level depends on the radius r, which is the square root of the number we're trying to represent. And unfortunately, it's actually done so in just a very precisely balanced way. That this inequality is minimized when x and r are of the same size. We do gain that bound in m that we're looking for to sum up over all the m that are non-zero. I can do that as soon as n is, say, twice a dimension, or actually just dimension plus 1. But I've not gained anything over the trivial bound of r to the d when x and r are comparable. And I go over this because this is exactly where it's useful to start doing the major arc, to split things into major arcs and minor arcs. So we choose some major arcs. Now, I pick a Farey level still to be x, which is some big number that depends on the number we're trying to represent, n. But I'm going to pick another number, y, which is much smaller than x, also depending on the number we're trying to represent as a sum of squares. And I'll define my major arcs as the Farey arcs, where I have a smaller denominator. And the minor arcs are going to be all the ones with big denominators. The way things end up working out is the minor arcs are going to be most of r mod z, of the torus, and the major arcs will be a small portion of it. And as x and y go to infinity, y, and as the way we'll take y, m of y is going to be tending, the minor arcs, the mass of the minor arcs is going to be tending to 1, which is the volume of the torus, how we've normalized it. Okay. But when we do this, on the major arcs, we actually now have a slightly different inequality. We get a y over r here, times an r, plus an r over x. So that when x is much bigger than r, we're getting some decay in the second summand. And when y is much smaller than r, we're getting some decay in the first summand. So that altogether, we get a bunch of decay by ratcheting up n as we tweak these parameters. So how do we actually put this into practice? What we'll do is to sum up over over the lattice. This is the form we had for our exponential sum inside the integral. Right? We had a Gauss sum times this Fourier transform. That's depending on n divided by q now. Just apply the trivial bound to the Gauss sums. Each one of these is bounded by 1. So the sup over all n doesn't matter. It's just 1 times the bound that we stated before for each of these Fourier transforms. Summing up, and then, sorry, above I had this factor of absolute value of m to the minus n. And again, as soon as n is large, like dimension plus 1, that's summable in terms of m, non-zero, and I just get a bound of this shape for the whole exponential sum around at a major arc, okay, and around on a major arc. That's a good bound for us as long as we can choose, say, y and r and x such that this sum is at most r to the minus delta. Because when I take n sufficiently large compared to delta, say it's going to be delta is, no, sorry, say n is such that delta times n is at least d. Then this term right here gets canceled out. This term right here cancels out the r to the d factor that we lost in the change of variables. And actually what we have is just all the non-zero frequencies are O of 1 on the major arcs. So as long as we can do this, this integration by parts has so much slack in it that we can really make this tiny, up to some implicit constants that do not depend on the number we're trying to represent, nor on y or r or x, or the major. So implicitly, it doesn't depend on the major arcs or minor arcs. Okay. Now we need to make sure this isn't a problem when we sum up over all the major arcs, and that's quite simple. You just you sum up and you see what you get. When we do that, because we can make this so small, it's gonna wash away any sort of addition of terms that are of the same size. And so you just apply the triangle inequality to cancel out, to get rid of this phase, move the absolute value inside, and apply the previous bound, which is right here. You remember what the volume of your I of a over q is. It's about 1 over q times 1 over q times x. But the number of a is about q. So this whole sum and integral is just 1 over x times the bound that we obtained before. And now there are only y many denominators. And y was chosen to be less than x. So this bound is at most 1. And we just have the same bound that we expected previously, or the same bound we got for an individual major arc. Again, there's just so much slack there, so much working to your advantage that it just overwhelms any possible difficulty. So I'll just write that down, just all together. We have the following. On the major arcs, when I look at the non-zero frequencies, I get this type of bound. And as a corollary, if I choose my y and my x as related to r, such that y is, say, r to the 1 minus delta, so it's a bit smaller than r as r goes to infinity, and x is a bit bigger than r as r goes to infinity, as say x is r to the 1 plus delta for some small delta. We end up getting, by choosing the right number of integrations by parts, we get that this whole error term on the major arcs is just O of 1. It's bounded by some universal constant depending on the number, on the dimension, and this delta that we chose. So at the end, we'll want to hard-code a delta in the proof in order to make this useful. Great. That is one error term for the major arcs that reduces the stall to 0 frequencies. Before further processing the major arcs, I just want to introduce Weyl's inequality and its proof. It was another wonderful thing in analytic number theory But as you imagine, it wasn't due to Hardy and Littlewood, it's due to Weyl. And it's an incredibly simple but powerful tool. The idea of it is, the simplest case of it is, suppose I consider a quadratic exponential sum. So I'm summing up n from 1 to r, where r is, say, some natural number. Now, and I look at this exponential sum where my t is near some rational number and my c is just some real number. Then it turns out that I can get a very good bound on this exponential sum. Again, there should be absolute values here. If my t is close to some rational number where the denominator is quite large. Large meaning comparable to, in some sense, the length of this exponential sum. And when that, and the actual quantitative bound is that right here. So the thing to pay attention to is this exponent of a half right here, and how it contrasts with this exponent of 1 plus epsilon here. The trivial bound in this exponential sum is just, again, I take absolute values, I move it to the inside, and all those exponentials are now 1s. And the length of the sum, r, is the trivial bound. So this bound right here on the right, if r to the 1 plus epsilon is a much worse bound than r, what we need in order to actually make this better than the trivial bound is q to be quite large. And when it is, what we end up getting, so it's quite large but not too large, we end up getting, say, if q is equal to r, something that is a factor of r to the 1/2, sorry, r to the minus 1/2 on the right-hand side. So that this whole exponential sum is actually of size r to the 1/2 plus epsilon, which is square root cancellation. And square root cancellation is the holy grail and half of mathematics. Right, as a special case to this Weyl inequality, let's just quickly deduce what happens when we actually are that rational point a over q. It turns out that just rewriting this inequality and using the fact that the exponential sum is then periodic in terms of t, you can break the sum from 1 to r into a 1 to q, q plus 1 to 2q, and so on. Use periodicity to show that this is the Gauss sums. The one-dimensional Gauss sum of this is actually q to the epsilon minus 1/2. And remember that I said that the Gauss sums are actually, the d-dimensional ones are just a product of one-dimensional ones, a product over the coordinates of b. This bound didn't depend on b, that c is just b over q, which is also necessary for the periodicity. And you get to amplify that bound to q to the epsilon minus d over 2. Right, one-dimensional sum was when d is 1, and we had q to the epsilon minus 1/2. Now we get, for d dimensions, q to the epsilon minus d over 2. And that implicit constant, it depends on the dimension, it depends on epsilon, but it does not depend on a or b or q. Of course, the bound here is explicitly in terms of q. And so there's a nice uniformity overall in terms of a and b don't matter. And that's a much better bound than the trivial bound of 1 that we had before. Again, a square root cancellation. We had the normalization was by q to the minus d. And so what it says that when we take into account the effect of the actual directions the exponentials take us, then we get a square root cancellation in terms of the number of directions, which is the most you can hope for in something, unless there is an incredible amount of structure that basically makes you 0. Then the best you're gonna ever hope for is square root cancellation. As a result, if we take as our choice of the major arcs and the Farey level as before for the major arc term, then we find that we end up getting a nice savings over the trivial bound for this exponential sum. Something that's basically r to the 1/2, but a little fudge factor depending on the delta. And even more directly than use of Poisson summation, much more directly than use of Poisson summation, you just get to apply Weyl's inequality directly inside the integral. I get to this HRTA plus Q is a product of one-dimensional things of this form. So when I take the absolute value, use a triangle inequality to ignore this factor to make it 1, and I just care about the absolute values of the HR, well, I get this bound over here, and it gives me essentially square root cancellation on the minor arcs. Just directly without having to go through the Poisson summation or anything. So this is quite useful. I've put in a couple slides to pause for a break. I think actually now is a good time to take a 10-minute break and finish this second lecture to move on to the third lecture when we come back. So I'll stop the recording now.